Okay, in this problem we have this small cart, 100 grams. It's moving at this speed on an air track, so it collides with a larger cart that's at rest. And then the question is about the collision. After the collision, the small cart recoils, and what is the speed of the large cart after the collision? So there's a lot of information in here, and kind of myself, as I look at this, a couple things that I notice is that right here in this number, we only have one significant figure. We have two here, and then I think this is implying that there's more than one here, but it doesn't matter. We've just got one significant figure, so there's a way in which we'll only report the solution to probably one significant figure. Normally I add one additional significant figure, so I'd probably report it to 2. So I'm just saying that so you don't have a great deal of anxiety about keeping track of the numbers. Okay, so then what I would do in this problem, as kind of setting it up, I would try to draw myself a picture of what's going on here. So there's kind of a before picture, and what I have is some cart, and we know this cart weighs 100 grams, and this cart is moving at 1.2 meters per second, and it's on an air track, so there's no friction. The reason I know this is because an air track would mean that the cart is sort of levitating, and so you could guess that there's no friction. Okay, so it's moving before at this speed, and then after, I'll draw a little after picture. What we have is that it has somehow collided with a large cart, or more massive cart, and this one now has a velocity, and the velocity is unknown. And also this cart, after it collided, the little one is actually now heading in this direction at 0.85 meters per second. So what I have here is a before and after picture, and what I know is that if we look at the momentum before, we know that it must equal the momentum after. And now the total. So this, in the case of before, this momentum here is just represented by this guy. We have this, I guess, if we could draw a picture, we have this 1 kilogram mass sitting here, but the velocity is 0. So this has a momentum equal to 0. So we know that the momentum before must equal the momentum after because momentum is conserved. And in the question, they're asking you, okay, what is this velocity of this big guy after the collision? So all we need to do is set up an equation that computes the momentum before and says it's equal to the momentum after, and then solve for the unknowns. And I think you could see in this case that we've got something goofy going on in that this cart starts out moving in this direction and then it goes back this direction after it collides. So this is a clue that you'll need to set up some kind of coordinate system. So let's say that this is an x direction, and we're going to define this as positive. We'll say that this direction therefore is negative. So let's go ahead and set up the equation, and I'm going to try to give myself a little bit of okay, here we go. The momentum before, we have m1 v1 plus m little plus m big v big. I'm going to call this will be the little object, this will be the big object, equals m little v little. Okay, I'm sorry, I need to add an extra notation. This is 1 1 1 1, and this is 2 2 plus m big 2 v big 2, and I'm using the 1 and 2 to differentiate between the before the collision and after the collision. So I'm calling this 1, and this is 2 over here. So in our equation, we know that the velocity of the big item is 0, so this whole term goes to 0. Now we have on this left side here that 100 grams, or 0.1 kilograms, times the velocity 1.2 meters per second, and we know that's in the plus x direction as we've defined it, so I'm making this positive. That's equal to now the same mass, 0.1 kilograms, times negative 0.85 meters per second, plus 1 kilogram times the unknown velocity. And I'm going to leave off the subscripts and just leave that v, since it's my only variable. So what I have on this side, if I multiply that out, that's just 0.12 kilogram meters per second, gram meters per second, and I'll add to it this term right here, which is a tenth of 0.85 is going to be 0.085. So I add 0.085 kilogram meters per second, and that equals 0.085 meters per second. That's equal to, you can see this is the only thing left. It's equal to the velocity. Oops, I'm sorry, kilogram meters per second. And the velocity times kilograms. If we divide kilograms out from everything, we end up getting just meters per second for the velocity, and you see that you just have to add these two values together, and we get the velocity is equal to 0.205 meters per second in the plus x direction. Whoa. So this velocity here is 0.205 meters per second. Now notice something about this velocity. This is a lot less than this initial velocity, and you might ask yourself, well, gosh, does that make sense? And you can see that this is a 1/10 the mass of this resting object here. So when it comes in and hits it, it actually bounces back, and with a velocity less than the original velocity here, 1.2 meters per second, and then causes this one to just move very slowly at 0.2 meters per second, much less than this velocity. That seems to be a reasonable solution.